We are going to find the step response of an RL circuit. In essence, we're going to find the currents and voltages through this inductor after we close this switch, as it charges up. To do that, we start by writing the KVL equation in this loop after the switch has been closed, and we would have it that Vs equals I R plus L di dt. That is to say, the voltage supplied is equal to the voltage drop across the resistor and the voltage drop across the inductor. We can then proceed to rewrite this as Vs minus I R equals L di dt, which can then be rewritten as di dt equals V of S minus I R over L. So let's do something here. We're going to factorize minus R out so that we have minus R over L equals V over R, that would be I minus V over R, which is equals to di dt. Recall that tau is equals to L over R. So we can write this as di dt equals I over Vs of R over tau, all negative. We can then say that di over I minus V of S over R equals minus 1 over tau dt. If we were to integrate both sides, this 0 to t, and this would be I of t to I naught. We would have it that log to base e of I of t minus Vs over R all over I naught minus Vs over R equals minus t over tau. You can then rewrite that as I of t minus Vs over R over I naught minus Vs over R equals e raised to power minus t over tau. This tells us that I of t equals V of S over R plus brackets I naught minus Vs over R multiplied by e raised to power t over tau. And this is the current at any point in time when we are trying to charge up an inductor. Now, if we wanted to know the voltage across this inductor at any point in time, we just have to recall that V of t is equals to L di dt. So what we just have to do is to differentiate this So the I t the t would be equals to minus 1 over tau into I naught minus V of S multiplied by e raised to power t over tau. Now to find the voltage, all we just have to do is to multiply this by L. If we multiply it by L, we would have that V of t would be equals to minus L over tau into I naught minus V of S over R multiplied by e raised to power minus t over tau. Now this is very interesting because tau is L over R. Tau is L over R. So L over R, L divided by L over R would be equals to R. So we can write this as R into I naught minus V of S over R multiplied by e raised to power minus t over tau. Then that would give us that I naught R minus, let's not forget this negative sign, there's another negative sign here, minus V S e raised to power minus t over tau. Then we can say that V of S minus I naught R raised to power minus t over tau. In essence, the voltage across the inductor at any point in time is this. I want to draw your attention back to the equation for the current across the inductor at any point in time. If the initial current across the inductor is 0, then that means that I of t would be equals to V of S over R minus V of S over R e raised to power minus t over tau. That is if I not equals 0. And in this case, after a time period of t has elapsed, that is t is equals to tau, after one time constant has passed, the inductor current would have reached 63.2% of its final value. So I'm just pointing it back to the significance of the time constant and how we can use the time constant to determine how long it takes for an inductor to charge up.